I wish I was in the fire, but this is what I know.
That's how you get your question. Oh, okay. I don't know. People shouldn't.
All right. I know there's some questions about number 6 on the FRQ. Let me. I'm going to come back to that. Circle back to that after I go over some of the particle motion FRQs. The parametric particle motion. So let's do those first, and then I'll come back. I know that, especially number 6, that general term is a little bit strange. So I'll circle back to that after I get through these some of these problems here. So let's go to page 7 in your packet. So the nice thing I think about particle motion parametric FRQs is that I feel like even if you didn't have any BC knowledge and you're just going in cold to this problem with just AB knowledge, you can probably figure a lot of this stuff out. A lot of this just kind of makes sense from an AB perspective, even if you didn't know. Like I feel like students who, if they were guessing their way through and they only had AB knowledge, they can probably solve a lot of these problems, which is good. I think that's nice. I think we like seeing like a parametric particle motion FRQ show up on the BC exam because it just feels like an easier problem. It's almost like a little bit of a freebie. Not all problems are going to be. Some problems are more challenging, but I think in relation to other FRQs, these are the ones that we'd like to see if it shows up on the AP exam. Okay, so let's start with. Okay, so let's talk through some of these problems here. I'm going to talk through 1 and 2, and then we can try some of these on our own as well. Now, this is meant to be non-calculator. Anything that is in that 4 to 6 range is definitely going to be non-calculator. I will let you use your calculator on your FRQ quiz, but I'm going to expect you to show all your work like as if you did not have a calculator. Okay, so number 1, a particle moves along the curve defined by the equation y equals x cubed minus 3x. The x-coordinate of the particle x of t satisfies the equation dx over dt equals 1 over root 2t plus 1 for t is greater than or equal to 0, with initial condition x of 0 equals -4. So part A, find x of t in terms of t. Well, if I want to get to x of t, and if I have the derivative, I can just take the what? Integral, right? So we're just going to treat this like an integral problem. We rewrite it. Okay, so once we're here, what's our next step? What can we go through?
U sub? Yeah,
U substitution. Yeah, and then once you go through your substitution, this eventually is going to turn into a what problem here? I have u to the 1/2 in the denominator. Eventually, that's going to. What rule do we use for that?
Power rule.
Good. Yeah, I got to bring it up, right? Bring it up. It's not natural law. I got to bring it up. Okay, so it's good, right? We're kind of reviewing a lot of this AB content. Okay. All right, let's go through. All right, so have you guys try it, and I'll work through it at the same time that you guys do. So I went through use substitution, power rule, brought back my original variable. How can I solve for C? What information do we have?
Initial condition.
Initial condition, yeah. So 0 in for T, -4 in for X sub T, solve for C, and then we can find the specific X sub T equation. All right, any questions with part A? Part B, find dy dt in terms of T. So we know it has to be involving derivative somehow. Let's see what they give us. They give us y equals x cubed minus 3x. But I want time to show up. So what can we do? Yeah, so this is a little bit of related rates here. We want to, oops. Anytime we want d over dt to show up, it's kind of like we want to apply related rates here.
Replacing everything with T initially and then finding derivatives work.
Yes, I think that can happen. I find it's a little bit cleaner though if we just start with this equation and jump directly to the t's showing up. Okay, so with related rates, that means we're going to find the derivative of each term, but as soon as we find each term's derivative, we're going to attach a d over dt for that variable. Okay, so y becomes what? 1, yeah, y becomes 1, and we attach dy dt. X cubed becomes
2x, yeah, dx dt.
good. Minus,
dx.
good. Okay, they want dy dt in terms of t. So I think we have everything that we need, right? We have x in terms of t. We have dx dt in terms of t as well. Okay, we'll just put all that in. It's going to look a little messy, but it's okay. They don't ask us to clean up. They just want our derivative in terms of a certain variable. So questions.
If I happen to get x of t wrong in A,
Mhm.
but like if I still correctly do B, with the wrong x of t, like will I still get partial?
Yeah, you'll definitely. I believe you'll still get partial credit. You may not get full credit, but it really depends on the rubric. But yes, they're always looking to see, do students understand the concept? If they're pulling wrong data and they understand the concept, typically graders will still are still instructed to provide partial credit. Now, how much partial credit, that's the discussion that they're gonna have. But you know that, yeah, the idea is that, you know, they're more interested in, and me as well, more interested in, and you understand the concept, and, you know, if you're pulling wrong data, you'll still get the majority of the points. All right, part C. Part C says find the location and the speed of the particle at time t equals 4. All right, so location for x should be pretty straightforward. We can use the x of t, and then for y of t, we can build it from what we have. So let's look at this one piece at a time here. All right, so location at 4. So let's see, x of 4. We can use the x of t that we've built from part A. Find the location of the x component at t equals 4. Now, we know y in terms of x. We can also call this y of t, and then x, we can just adapt it here, call it x of t cubed minus 3 x of t. All right, use this to help us find y of 4, right? Replace every t with 4, and then we can grab x of 4 from above. Replace x of 4 with what?
-2.
-2. All right, bit of a reminder here. Speed has a certain formula. Speed is the square root of x prime of t squared plus y prime of t squared. So we want to find the speed at t equals 4. So replace the t with 4. And then we can just gather this from before, right? We have x prime of 4. We can build y prime of 4. I'm sorry, we don't have x prime of 4, but we can find it easily, right? We have dx dt, so we can find x prime of 4 using dx dt. And then we build y prime from part B, so we can just plug in 4 and find that. It's a little messy, but we can do this without a calculator, I feel. As a reminder, this is non-calculator. So what that also means is that your answer can be unsimplified and they'll still give you full credit. So dx dt, we have dx dt at the beginning of the problem. Replace t with 4, we get 1/3. Dy dt, that mess that we built in part B, We can find that to clean up to all the way down to 3. So root 9 is 3. 3 minus 5 is -2. -2 squared is 4. 4 minus 3 is 1. Wait, I'm sorry. I got to multiply by 3 first before I can subtract. Okay, so 3 times 4 is 12. 12 minus 3 is 9. 9 over 3 is 3. Okay, so I have x prime of 4 being 1/3, y prime of 4 being 3. Speed, you can leave it in this form, but if we were to clean it up, it would get all the way down to root 82 over 3. Okay, page 8, number 2. Okay, again, non-calculator. Anything that is 4 and above is going to be non-calculator. About 15 years ago, 10 years ago, they changed number 3 from calculator to non-calculator. So yeah, in more recent years, it's just number 3 will be non-calculator, but early on, number 3 used to be calculator. No questions? Yeah. All right. Right, a moving particle has position x of t, y of t at time t. The position of the particle at time t equals 1 is 2, 6, and the velocity vector is given by u of t here. Okay, find the acceleration vector. So we can just take the what? Derivative of both the horizontal and the vertical component, right? We wish all FRQs are as straightforward as this. Okay, to get the position vector, we can do what?
Integrate.
Yeah, integrate it, right? And then a plus what will show up? Plus c, yeah, and we can use the yeah, we can use the order pair to solve for c, and then we can build the position from there. should be more specific here. This is represents both x of t and y of t. The position particle position component has the horizontal vertical, so I should call this x of t, y of t. So use the given information to help us solve for C. We know that when t equals 1, our x of t, x of 1 is equal to 2. Can leave that 0 out. We don't need that 0 there. Again, this is non-calculator, so we could leave our answer unsimplified, and that would still be fine. Okay, part C. For what time t does the line tangent to the path of the particle have a slope of 8? So, how do we represent slope?
dy for dt over dx over dt.
Good. So we know slope is normally dy over dx. We can expand that or give it a little bit more detail, right? We can make this in terms of time. We can say dy dt all over dx dt, right? So this is our adapted formula that we can use to help us find what we're looking for. Well, we have dy dt, we have dx dt. We'll put those in place. Those are the velocity, that's part of the velocity vector from the beginning of the problem here. We can set all this and set equal to what? 8, yeah. I'm just going to cross multiply and algebraically solve for t. So cross product there, distribute the A through, get the T's together. Solve for T. Okay. Normally, if we take square root, we have plus or minus, but in this case, why is it only the positive? Yeah, restriction, right? We have time t greater than 0, so prevents us from using the negative value. Any questions, part C? Part D, the particle approaches a line as t approaches infinity. Find the slope of this line. So it's kind of like finding horizontal asymptote here. Show the work that leads to your conclusion. So we just, how would you set this up? Take the limit, yeah, take the limit of your slope from part C of your dy over dt over dx over dt, and look at what that relationship will give us. So as t approaches infinity, what's going to happen to this fraction here? 0. Right. That denominator is going to get larger and larger. This will go to 0. And this is also going to go to 0. So limit is just 1. And yeah, just equal to 2. Yeah. Yeah. Every now and then you have some problems that are your part C and D are not that challenging. It just depends on the problem. But usually the pattern is the problem is going to begin or going to continue building until part D, where it's just going to feel more challenging. But sometimes you have a problem that's just it's not gonna feel like that. Okay, so I think we have a lot of the background that we need to help us through. So if we can go to page 9, number 9 is page 9, number 3. Okay, this one is 2001, number 1. So this is what? It's a calculator question. Yeah.
For calculated questions, the answer needs to be simplified.
Yes, yeah. If it's calculator, they expect you to plug in and get some decimal value. Yeah.
Wait, how do we know that it's calculated?
Yeah, so this is 2001, number 1. Anything in the 1 and 2 range is always going to be calculated.
Okay.
And then the 3, about 10 years ago, is swapped from calculator to non-calculator. But for 1 and 2, you know for sure it's going to be calculator. For numbers 4 through 6, it's also guaranteed to be non-calculator. Okay, so try part A. Write equation for line tangents. So find your slope. Have your ordered pair. Point slope form. Right, always in radians. So your calculator, we should always be in radian. But having said that, radian only matters if we're dealing with trig. But we just always tell students, always leave in a radian mode, that you never have to worry about going back and forth. And we're never going to be in degree mode. So, but yeah, I would say always leave in radian mode. But ultimately only impacts trig. So dy dx can be broken down into dy dt over dx dt. We can, there's no need to even do anything. Without doing math 8 or any of the calculus features, we can just, it's already in derivative form, so just have to do direct substitution, replace your t with 2, get your slope, take your point, and then point slope form.
So is it fine to keep that, like the, slope to be exact,
Like that.
yeah. You can't really simplify it.
Well, I would say if it's non-calculator, then leaving like this is perfectly fine. But with the calculator, I think they expect you to go a little more and get that decimal value.
But if it's a unit circle value, like,
Oh, you mean like sine of like pi over 3 or something?
yeah, then I should simplify.
Yeah, then you would want to simplify. If it's like sine of pi over 3, then you want to use, then if it's non-calculator, you definitely have to get it down to a ratio. And part B, find the speed. So we talked about the speed formula, square root of x prime squared plus y prime squared. Distance kind of feels like the speed formula. It's just basically the speed with integral notation. And it kind of makes sense, right? We know speed is related to velocity. We know the integral of velocity will give us something in that displacement distance realm. So, if we know the speed formula for parametric, we should be able to use previous knowledge to understand, okay, the integral of that will give us distance.
That would also be the total distance, right? Or
It is total distance, right, total distance. Not displacement. Okay, all that goes in your calculator. Practice entering that in. The way that you have to enter cosine squared, you have to put it. There is no notation that allows you to get that squared in that place. So you have to do cosine of x cubed. That's the only place to put it. And we don't. Our calculator is not able to put that exponent in that shorthand form. So you do need a second set of parentheses. Or if you want to let cosine x cubed and sine of x cubed of x squared be stored under y1 and y2, then you, but maybe it's just easier to just put it all under the same line and just have additional set of bracket parentheses. Okay, part D. we have that, we have that Parker motion formula, right? Final position equals initial plus displacement.
Remember like for final position, like there's like multiple formulas for it, so like I don't know which one to use. I remember like in the AB FRQs, there was like a different formula.
I mean, I think this is all just a rearranging of first theorem. I mean, if we want to write it as A to B of F prime is equal to F of B minus F of A. And it just inserts the pieces where they go and then solve for the missing variable. We can as well, but it's just rearranging of first theorem. So, I mean, if we want to do this, if we wanted to say, we know that this is going to involve so starting at 2 and ending at 3. So if we want to say, okay, from 2 to 3 of x prime, and this will be x of 3 minus x of 2. So if we feel more comfortable just writing it out in this skeleton form, and then just putting the pieces where make substitution and solve for that missing variable, we can do that as well. Right, we have x of 2, we can figure this out and we can solve for x of 3. Or for on the y side, we can plug this in the calculator. We have y of 2, solve for y of 3. Okay, let's spend a few minutes to start page 10. This is the last problem for your homework, so get a head start with it in a few minutes. Let's get the phone.
Problem 6.
Yeah, I didn't get a chance to get to that. Let me do that first thing Monday. Oh, yeah, I'll do that. So this is what we're working towards for next Thursday. So next Thursday, you'll have a test, one of these problems and one of the series problems. And then that's going to be buffered by your homework grade as well. So then should feel pretty comfortable once you get to this.
Only 2 questions.
Just 2, yeah. Plenty of time.
And they'll all have like ABC.
Right, something like that, right? It's gonna be one of, it's gonna be very similar to. No, I'm giving you guys more time. Yeah. But I think, you know, after we do 2 months of it, I think your speed will just naturally go up.
Speed,
15 minutes on average per problem
on the.
on each FRQ, yeah. But some FRQ are fast, right? This should be fast, which means you can spend more time on the other.
The hard.
Right, hard. Okay, computer phones. So on Monday, I'm gonna check pages 7 through 10. I didn't forget about number 6. I will go over number 6 and we'll just continue working through our packet.
I studied this well. I'm not saying.
Yeah, you said.
It's acceleration vector. So we want both the horizontal and the vertical.
Yeah, they do. That's what I'm trying to do.
Oh, sorry, this week too. Right, thanks.
No one ever talks for the natural law. Never.